Thank you everyone for being here. Today I want to talk about a package that we wrote not too long ago. I think over this last year we've been working on this package called Inti. So this is work in collaboration with Thomas Anderson, who is a professor at Rice, and Carlos Perez Arancibia, who is a professor at Twente. And my name is Luis. I'm a research scientist in France at this INRIA Institute. So that's why all the logos. Okay, so let me I think this will be a little bit of a technical talk in terms of the math, so I'll try to go maybe not so fast. So Inti is this, like I say, library to solve these things called boundary and volume integral equation methods. So we include sort of high order schemes that's really close to our research, so we hold that it's important for us. We have support for this so-called acceleration methods. We really wanted to be able to handle both academic problems and also sort of big industrial size problems of including complex meshes. There is some documentation, and you can go through the online documentation. Of course, it's not complete like any documentation, but should be fine. Okay, so I guess if I manage, first question is why would you want to solve an integral equation? So there are many PDEs actually. So these are kind of niche methods, but when they apply, they can be very, very useful. So there are many PDEs that can actually be recast in terms of these so-called boundary integral equation methods. Okay. And when you can do that, it leads to really highly efficient solvers. So this is an example of a simulation of some sort of acoustic scattering, if you want, of an airplane. Three-dimensional simulation. We've visualized the pressure field across a plane. And these simulations, you can run them, on a decent laptop or like a reasonable desktop if you're sort of using these methods. Okay, and I'll try to explain why that is the case. So the second question, why Julia? So yeah, why boundary integral equations? That's what I work on. So why Julia? Well, we found the ecosystem for the scientific and numerical linear algebra to be quite good. Actually, it's also very composable, easy to build abstractions, which we will need because these methods tend to be complicated. We found the syntax to be kind of user-friendly compared to, say, C++. And we really needed the ability to write fast code where it mattered. So in Julia, we found that this kind of, we had everything that we needed in there. So let me just go through an example of what the syntax kind of looks like. So the first line is, I think it highlights composability. So we're actually not going to code lots of the things here, like iterative solvers, we're not going to code them. Or these H matrices is some sort of way of compressing some big dense matrices, okay? There's the gms.jl package that allows us to handle meshes, to visualize things. So the first line is, I think, a good showcase of how Julia allows for this type of composability. So kind of standard when you're solving these, say, physics-driven problems, you have some sort of representation of your geometry, you have to mesh it, way focus on the solver, of course, and then you have to post-process, maybe using Mackie, maybe using some Paraview, you export a Paraview file, so that's kind of up to you. So the usual stuff, you import a mesh, this is a Gmesh file, so if you're not familiar, it's just a mesher. Then you sort of extract what is your domain, omega, so the interior of this sphere. Then you have to look at the boundary, you have to build some sort of quadratures, and these are sort of the main focus of the package, and I'll try to explain a little bit of the method behind it, because it may not be so clear to everyone, what are these single double layer objects. And then you can kind of just call an iterative solvers, you build some linear map, so these objects are actually, you can just lazily compose them, mostly thanks to linear maps, so we just build on top of that. And you can solve, say, a scattering of a sphere, so in this case it's a bit simpler than the airplane, but this one runs maybe in about 5 minutes, so it's a 3D, relatively, not high frequency, but not super low frequency either. So I think that's sort of an example. So now I'll sort of try to convince you in the first section why these type of methods are perhaps interesting for some applications. Then we take a sort of quick look at the main structure of Inti, the high-level API, and how we build these things. Then we go through some documentation, examples, roadmap, conclusions, and let's get going. So in a bit more detail, what I said earlier is that usually for many PDEs, you recast them as these integral equations. Examples that I just show here, so Laplace, Stokes, Maxwell, you can do elastostatics, elastodynamics, so as long as they're linear piecewise constant coefficients, let's say the methods are useful. So the main advantage is actually that you just pose your problem on the boundary of your domain. So that's why we have less degrees of freedom. And that's why you usually can hope to be more efficient. So if you're in 2D, if you imagine in 2D, instead of having to have n by n degrees of freedom for a square, you just have n, or for n, for the sides of the square, okay? So you can sort of hope for this linear, quasi-linear complexity, where linear means in terms of the number of degrees of freedom of your boundary. Now, of course, that comes, so the main advantage, I would say, is this one. And then there are sort of more technical advantages that you actually exactly solve the PDE, so you don't have these errors called dispersion errors. So what you construct is an exact solution. The drawbacks, of course, there has to be some drawbacks, is that, yes, you have n by n systems, but they're dense. So these are dense matrix, so if you're just trying to store them in memory like that, or do operations with them, factorize them, that would cost too much. And the second difficulty is that actually the operators you're going to write have some singularities that you have to handle. And I think this is sort of one of the main reasons why we don't see these methods too often used in the wild, even when they are probably one of the best choices of methods that you could use for those problems. So they're not applicable to many PDEs. So this is by no means a competition to like finite element methods. It's just for some PDEs, it's an alternative. Okay. So I think this is sort of the drawback that we observe, and we do research in that, and we thought it would be nice to try to take a step closer to people who actually want to solve some PDEs. So let me be more concrete and show through a simple example how do this type of methods work. So suppose a very simple problem. You want to solve a Poisson problem with Dirichlet boundary conditions. So omega is your domain, and the notation will be that gamma is just the boundary. Okay. So the usual thing that you can do is you can just first build a particular solution. So that means that it solves with the f right-hand side there, but it doesn't satisfy any sort of boundary condition. So that's just a convolution of some sort of special function. So this is the Green's function. And I wrote here where it is for Laplace 3D. So it's kind of Newtonian potential type of things. And the important thing to notice is that this function is actually singular when x equals to y. So that's one of the difficulties I mentioned. And the second one is this function is never 0 for x and y. Okay, so that's the dense matrix. So dense, this function doesn't vanish. Interactions arbitrarily far apart. Well, it decays, but quite slowly. Okay, like 1 over r. And the second one, it's singular, so integrating these, you can imagine like standard quadrature rules are going to have a problem. So coding this gets a bit tricky, let's say. So the first part, you sort of build this particular solution, and then it doesn't satisfy the boundary condition. Then you have to come and sort of correct with what is called a layer potential to take into account the boundary condition. And this sigma is some layer density, so this comes from physics. It's a single layers, where people kind of put monopoles. You can conceptually think about putting monopoles on your boundary. Okay. Now this is only integrating over gamma. So once you do that, you actually construct a solution to the PDE without, say, only having these integral operators. Now this was Laplace, and you can more or less generalize these to L. L has to have some properties like strongly elliptic systems, things that would be fine. You can generalize boundary conditions. This is like a Dirichlet and a Neumann boundary condition. So you can more or less do this for like a wide class of problems, but you keep on running into this type of objects, so volume potentials, which are integrals over your whole domain, and then boundary potentials, which are integrals over your boundary, of the singular functions or derivatives of those singular functions. Okay? So not really important, the notation here is just to say that we more or less understand what are the building blocks for these inter-equation methods, and they're really built around these 5 integral operators that I wrote here. And the purpose of the package is really to provide you a way to accurately and sort of quickly evaluate these things. So you see these are sort of non-trivial tasks because accuracy, you have the singularities, and quickly you have the dense matrices. So you have to do something with it, otherwise these methods are not practical actually. So let me just go take one word on the discretization schemes, since it's not probably not a very well-known method. So suppose I want to solve for u in an equation of this type. So I have I don't know u, I'm given f, I'm trying to find a u that solves this inter-equation d some domain. It could be omega c or just the boundary. Well, what we'll do is we just approximate this integral by some quadrature rule, not saying how you build that, but you have some way of integrating over this domain d, and then you just replace the integral by a sum, okay? And once you do that, you have to sort of figure out how do you compute the values of u at the unknown at these quadrature nodes. And you can, these type of methods that we implement, they will just impose a strong equality at the quadrature nodes. and then you solve the resulting linear system. So now this is just a linear system, which is identity plus some dense matrix equals to F. Okay, once you solve it, you have your solution, essentially. And this is what is typically called an instrument discretization scheme. So I'll come back to the challenges, and so sort of, I think this explains a bit of the structure of the package. So I'm not going too much into the usage of the package. I think the documentations are for that. I'm trying to give the sort of the conceptual design here. So we need to approximate objects of this type, okay? And these approximations need to be efficient and accurate. And typically what is done in the community is that, well, you have this sort of sums of lots of, so this is conceptually a dense matrix, and there are methods that actually can compute these sums quickly. Okay, so examples of these methods are the fast multiple method, hierarchical matrices, and there are several others. So everything in blue is implemented in Inti right now. And then these quadrature rules here, which are just sort of a standard naive quadrature rules for integrating, say, polynomials, they are not accurate near the diagonal of the matrix, just to make it simple. And then you have to come and sort of correct with a sparse matrix. Okay, so this other object looks like a sparse matrix. And this is what I'm saying here. Typically, the cardinality of the correction points is much smaller than the degrees of freedom. And this is really the central design. We want to be able to plug in different types of acceleration, different type of corrections, okay, because in some applications, you're better off doing one or the other. So what are acceleration methods? They're just sort of very clever algorithms, usually tree-based algorithms, for computing sums of this type for some sort of well-known kernels. They rely on some analytic properties of these kernels. The important point is that they're able to compute these sums. So you evaluate this matrix, which is conceptually an m by n matrix, and you can multiply by a vector in something which is linear or log linear, the size of the matrix. Okay, so it's kind of, if you want FFT, would be something that does that too. But this doesn't have the structure of FFT. Okay, so there are some other methods. The input. So I think this part of the code is kind of very well established. The input for this type of accelerations, you have to tell me what's your function, where do you want to evaluate it, where do you have your source points, and what are the source strengths. And then just output the values of these sums. And from a software point of view, this was actually relatively easy to get right, I think, in the library, because the interface is very clear. We didn't code most of the methods I mentioned, we didn't just code them, but there are wrappers available, there are Julia wrappers available, and if they're not, we can always write one. So this was, to get it right, we just hook into existing code. We don't want to reinvent the wheel, actually. So that was relatively fine. And this is very crucial for the performance, because if I deal with dense matrices, I mean, forget about it in terms of memory and in terms of efficiency. So we cannot redo that. The methods lose all sort of practical interest. And the corrections, on the other hand, they're kind of this difficult to state object that I write on the right here that sort of says, well, you have your integral, and you want to approximate it by some sum of a standard quadrature, but then it's not always quite right, and you have to correct for it, okay? And these are, I think, very difficult to state the method here. I won't try, okay? This is really, there's several methods that you can try. Usually they output some sort of sparse matrix. You can at least reinterpret them like that. The approximation properties are difficult to state. All you hope is that this, with this term, is better than without it, okay? So the approximation is improved in some sense. There are many methods available. Usually there's no software that goes with it, so we had to code it. And I think from a software point of view, I think this is sort of the ugly part of the library. Every method gets its own kind of interface. Like you have to read the doc of the method to decide. Okay, so there's some reasonable defaults, but yeah, this part is something that requires, I think, a bit further work to define what we really mean by these corrections first, and then maybe try to implement a generic interface for all of them. And this is, of course, crucial for the accuracy. So, I mean, getting solutions quickly is important, but they better also be right, otherwise it's not very useless. It's not very useful, okay? So, yeah, the main goal is really to be able to compose. What we wanted is that you should be able to switch between different methods easily. We want to be able to compose these operators, so I showed very simple examples, but the moment you start to mix boundary conditions and different PDEs, you have some elasticity problem coupled to acoustics, okay, then you may need to start composing these objects. We want to handle complex geometries, and we want to do so efficiently. So that led us to try and decide and write a package. Okay, so that was it with the sort of mathematical preliminaries, and now we hopefully have an idea of what these objects are, single, double layer. So there is a very high-level API, which is really designed around most of the problems we solve in practice, in our research. which are sort of PDEs, relatively simple PDEs, I should probably say. So the API, the very high level, really revolves around building these 5 integral operators I mentioned. So single, double layer. The others have a different name. Doesn't matter what they are, but you can always build them, and they kind of look the same. You have to say where do you want to evaluate it, where do you integrate over, what's your PDE. This PDE comes with some parameters. So if you're doing Maxwell, if you're doing Stokes, the keywords would be different. And then these 2 parts over here, which is what we really wanted. We wanted to be able to switch on and off a fast multiple, exchange it for maybe a hierarchical matrix approximation. So that's the joint double layer, and we use a different correction here, for example, and you have some sort of parameters for these corrections. And then just the volume potential, which is very much, I guess if you see from far away, they all look the same. Internally, volume potentials are different than these boundary integrals, but not. Okay, so currently we support these PDEs. I think they're fully supported, meaning they have acceleration corrections in 2D, 3D. But then I guess I could always just wrap very ugly code into that API, and it wouldn't be a very composable library. So what do you do if you actually don't have one of these PDEs? You have your own kernel, you somehow had your PDE that you found a fundamental solution, and you want to use the library? Well, so almost everything in the library, it's not the first slide we'd call the show, but almost everything in the library revolves around this object, which is the integral operator object. Kind of makes sense from what I've been talking about. This is our central object, and this is the central structure of the package. And at the high-level API, all it does is just actually provide some syntactic sugar for, you give me the PDE, and I know what the Green's function is, because I hard-coded it for you. I mean, I looked up some old book and found very ugly expressions for some of these. And then I pick an acceleration method. So there are several functions inside, like assemble H matrix, assemble FMM, that take some parameters, and I try to make them more or less uniform for the user. Then I pick a correction method for you. So how do you compute this accuracy? So these sparse matrices that are intended to improve the accuracy of your method. And then I just sort of wrap everything around. Maybe I wrap it around a linear map if I can't really have a good direct solver for you. Maybe I wrap it in some other object that would allow you to do an LU factorization. Okay, so depending on the acceleration methods that you ask, you may actually have no matrix whatsoever. Okay, so there's no full algebra that you can do with these objects. All you can do is just multiply by a vector. And then you are sort of forced to have an iterative solver. So that's all that we do. So if I suppose that you have some kernel that is not one of the ones I coded, so just take a simple one, which is, so this is, it's called directly Green function, but you just have some custom kernel if you want. Well, you have to define your own kernel here. So this is just saying you have some function that takes a target and a source, and there is a parameter for this one, which is k. And then, well, this is just boilerplate because I need to create the mesh and the quadrature and all of that. So we have a kind of, for simple surfaces, simple curves and surfaces, we have kind of an internal representation of geometries, which you can just write what your curve is if you want, and and then we'll handle the meshing for simple problems that works. Actually, for most of our research papers, this is enough. And then at the end, you actually instantiate this integral operator, okay? And then after you have the integral operator, you have to do these 2 parts. You split it into 2 parts: the dense part, which you compress, and the sparse part, which you correct. And this is an example of if you call. So this is what the API does. We're just doing it directly. You call this assemble H matrix, and this creates this hierarchical matrix object, which, as you can see, is a 3-data structure. Okay, it has some leaves, it has some dense blocks, some sparse blocks, some data sparse blocks. And this is sort of giving you some information of how much did you compress this full matrix, actually. And then the second step, like we said, is that I had this sort of S0, but it wasn't a very good approximation to my operator. So I have to build some correction. And we see here that the correction is just returning a sort of simple sparse matrix structure. Okay, so there's some code that will hopefully give you high order conversions and give you accurate approximations. And then after you're done with that, you can just combine them. How do you combine them? Well, you can maybe just wrap them in linear maps and use an iterative solver after that. So with that, you could essentially have your own kernel and plug in. And I know this is not it's not like at the console level, but it's difficult to I mean, I think it's difficult to go all the way to the just PD and boundary conditions, because I think, at least for now, would lose too much of the flexibility that we want to have. So you have this modular way of assembling these generic integral operators, but you still have to do some of the lifting. Like, you still have to understand how these methods work, reformulate your problem as a boundary or volume integral operator problem. Okay, so it's not a, at least for now. I mean, at least for now, it's not given. Right. So, but you do have this modular way that you can create things. So conversions are things that we care quite a lot about, because we do a lot of work to have these corrections, to have them be high order, to have the methods be accurate, so that you have, for example, fewer degrees of freedom. And I guess one thing that I found a bit difficult is, how do I check that my methods stay high order? So I have, of course, we have unit tests, but it's really hard to sort of track convergence rates. Like, is this, I mean, when we published the paper, this was a high order method. We have the figure, we showed it, and then we tweaked things here and there. Did I break the convergence rate or not? So it's something that we are, for now, so it's really difficult to unit test these things. The solution we have for now is there is sort of a separate dedicated repository that with every tag, we run some sort of convergence tests. Okay, so this is sort of classic convergence stuff. We expect, say, a fifth order convergence of this method as it goes to 0. This takes some time to run. Okay, so we don't run them on every commit, for example. But still, a human has to sort of come and look at this and say, yeah, you probably didn't break it. Okay, maybe we could compare images to some saved versions of these images, but we don't do that yet. So I think this is all auto-generated. So it's actually just a package that generates a documentation that puts these figures in. Okay, and I think we still have a lot of work to do. I'll be sort of happy to see how people track high-order methods and make sure that they don't break as the code evolves. So for performance considerations, I've been sort of saying that we want to be performant. So most of our performance is actually derived from libraries that we didn't necessarily write. We actually just wrapped some of these fast multiple libraries, for example. Okay, so you do have the choice, and some problems will be better with one tool than the other. We do efficiently implement these sort of correction methods that we have. The runtime overall appears competitive with other things that we had in our research, so old code written in Fortran or things like that. But I think there's still, of course, much work to be done, and it's by no means complete. Okay, we don't have a automated way for now to track performance regressions. I know there are packages for that, but we just didn't do the work required. And now, I think just to show what the documentation looks like, maybe some examples. I won't do a live demo, so there are the first sort of, this is really scattering 101. This is the prototype of a problem where integral equations are probably the best tool you can find out there. So you have some Helmholtz equations, so this is time harmonic acoustics, and you have some obstacle, so a ball or something, and you have a wave, say a plane wave coming into this, and it hits the obstacle, it diffracts it, it reflects, it does all sorts of things. And I think I need to, so this is what the documentation, apologize for this. Maybe I should have done this full screen like that. Okay, so we have some examples. Someone mentioned, I think, literate before. And so the examples in this package, they are sort of auto-generated using literate. So this is an example of, there's just a JL file somewhere that gets converted into this markdown with the documented syntax, and then there is some Jupyter notebooks that one can read. And that's sort of an example of how you'd solve this in real life. And when you may actually want to not, because of flexibility, you may not want to mesh things by hand. You may just want to use a mesher. So this is composing with this gmesh.jl. So you could create possibly very complicated meshes. This would mesh your surface, and then probably just solve a scattering problem or move a bit. I think we're just trying to compare to exact solutions, so that's why the example is a bit long. There are some exact solutions that you can figure out for simple geometry, so just to have an idea of what are the errors that we are committing. So yeah, so you can solve scatters in 2D. You could have more complicated objects. I mean, these are still very simple, but so that the documentation, and of course you can do it in 3D as well. It's just a matter of changing one parameter, one keyword, and of course be more patient with the time they would take. Okay, of course this is not going to be at the same speed 2D or 3D. So that's kind of the Helmholtz example that I showed. And then the second one is this Poisson problem that I explained at the very beginning. Yeah. So for the Poisson problem, yeah, I'll probably not go too much into detail because I do want to take some questions. It's very similar in nature. I already explained what we do of building a particular solution and a homogeneous solution to the problem. And then there are all these geometry meshes. I think it's a quite flexible mesh data structure that we have because we need conformal meshes. So for these high order methods, you better actually also mesh the boundary to high order. Otherwise, it's not really interesting to have a high order. I mean, maybe, but for the scattering, having at least a P2 or P3, so at least a curved mesh is important. So we can handle these curved meshes. We can also handle conformal meshes and things like that. So yeah, you build these integral operators. There are some GMRS going on in there, and you can just at the end again sort of compare the error, and it's usually pretty accurate. These methods tend to be pretty accurate when they work. Okay, so with that, I just want to probably to wrap up. So this is a more technical example that I'm not going to go into in the sake of time. So roadmap and conclusions. We released the sort of version 0.1 a couple weeks ago. 0.2, we're working on it. I mean, there's some new methods that we have developed that we want to put in. Okay, new methods that we have recently published that we want to put in there. We kind of want to finalize this infrastructure for automated tests. Of course, we should be tracking performance, otherwise we have a big risk of regressions. There should always be more examples. This is not so clear. I mean, should we really take a step even further and try to say, just give me the PD and the boundary conditions, and I'll pick a formulation for you? I don't feel very comfortable picking a formulation for you just because it's really problem dependent, but maybe we should. That way we get users who don't know any of these objects that I mentioned. And of course, we're looking for community feedback. I think that's why we decided to come and give a talk here. Yeah, so with that, I'd just like to thank you and take a couple of questions this time.
Two quick questions.
Sure.
Firstly, do you support also Neumann boundary conditions?
Yes.
Okay.
Definitely.
And is it possible to connect Inti with differential equations to solve evolution equations or evolutionary equations?
Like DFQ or like DFQ, for example? It should be possible. I think it would require some understanding of how the library works, but I think it can be used as just a black box. Like, give me the boundary conditions, I give you what the solution is. So there's no. So when you ask if we support Neumann boundary conditions, we do, but it's just because the whole theory of inter-equation supports it. So you can always reformulate even Neumann boundary conditions, even more complicated Robin or so yeah, that's why I say we support it, but yeah. There is a problem here where I think we do Neumann boundary condition in the documentation.
How general is your support for like various quadrature methods? Like if I were to throw some, I don't know, some like sparse grid or small yak type thing onto it, would that also fit into the API?
Yeah, so it wouldn't fit into the highest level API, which actually just asks for a quadrature order. So if I go through maybe basic usage here, the highest level thing just asks for, when I create a quadrature order. So behind the scenes, what's happened is that we have sort of a bunch of quadrature rules. Actually, that's very close to what we need for the singular integrals. So they're very specialized quadrature rules, and given a quadrature order, we pick what we think is kind of a best quadrature for you. But if you have your own preferred quadrature rule, it fits into like let's say the mid-level API. Like you wouldn't have to go really deep into the code. But when you construct this object over here, you just have to pass your quadrature rule specifically instead of an order. And of course, that has to adhere to a certain interface.
Hello, thank you for the presentation. This might be a very dumb question, but I'm going to ask you anyway. I saw that you managed to solve the Helmholtz equation. Would you be able to apply the same methodology to solve a time domain wave equation instead of a frequency domain?
So you can do what they call retarded potentials to solve a time domain using inter-equations. We don't support that. So the other way to no. So this package, I guess the short answer would be no, not directly.
Right.
You have to use something called convolution quadrature methods, for example. So there are methods that are going to recast the time, so the time-dependent wave equation, into a sequence of time harmonic wave equations. Then you can do essentially an FFT to go back to time.
So
But
what
yeah.
is the name of the thing that you said?
It's a convolution quadrature.
Convolution
Usually
quadrature.
CQM, so convolution quadrature method.
All right.
It's, I think, one of the most popular ones, actually.
I have another question. Would you
Yep.
be able to describe a function that, for instance, it has a Dirac delta, for instance, a singular point in space or something like that? Would you be able to express that through the package?
I didn't understand the question, sorry.
For instance, like if I have a function that is just like a value in a singular point in time in space, for instance, like is 0 everywhere or 10 in x equal 10 and y equal 10, would you be able to express functions like that that are impulsive with the package? No, right?
So is the solution that behavior? Is it what the solution
Not
wants
a
us-
solution. For instance, a source term or something like that. I don't know the expression because I saw partial differential equations, not integral equations. I'm not too sure about it. We can talk later. Don't
Sure,
worry.
yeah,
about
yeah, that'll be
it. Yeah. Thank you.